Welcome to the fifth Prodrive software meetup, where we are going to talk about creating a bug-free FPGA design within 1 hour. This is a summarized version of the presentation that was given live at Prodrive. First, let's introduce the speakers. First, about myself. My name is Frey. I'm 34 years old and working at Prodrive since 2007. And mainly on FPGA since 2009. And I'm also quite heavily involved in the FPGA design process. And my fellow speaker is Guido, 26 years old, working at Prodrive since 2017. He's worked on FPGA designs for motion control and cameras, and is, as he says, passionate about formal verification. So he will also be telling about that. Yeah, first. The FPGA at Prodrive. First of all, we are a hardware company, which means that we make products, and designing FPGA firmware is not really our core competence. Although FPGAs are part of many products, but we're not like an IP design house or something. But yeah, we do use FPGAs a lot, and there are key components in, for example, power conversion, motion control, and real-time image processing products. And FPGAs often form the heart of a system, being a big part of the architecture of the total system, because of course FPGAs interface not only directly with the hardware, but also, for example, the software, and there's maybe even the user. So so the FPGA is usually a central part in a product. And with FPGA design, there are several challenges. One of them is that, it's quite niche, really. So we're using languages that are, well, not used as much as, for example, C or Java or whatever. We use niche languages and also tools. And one of the consequences is that there's quite a bit less innovation in that compared to, for example, software design. There's stuff like high-level synthesis, but it's not always suitable to use. And FPGA and software design are quite similar, but many of the tools and also the infrastructure that exist for software design is not really there for FPGA. Another challenge is the ever-increasing complexity. So the chips get bigger, more integration with the CPUs, for example, but also just the FPGA projects we do at Prodrive become bigger and bigger. So team sizes become bigger. There's much more logic involved, maybe multiple FPGAs and multiple boards. So just basically general increasing complexity. And one thing is that FPGAs are particularly hard to test and also debug on hardware, because of course everything happens inside a chip and you can't really probe it or whatever. So that together with also the demand for example, shorter lead times means that there's a greater need for verification as well. Where did we come from with FPGA design? Quite a long time ago already. We started with a graphical design entry. We did not have any source control, or only very limited on the network drive. We didn't really do reuse, so everybody was basically just reinventing the wheel. We didn't have a verification process. So basically this process was just not suitable for the increasing demands that I talked about just now. The old way of working, it worked for small teams and small projects, but just not for big projects with multiple users and shorter lead times, for example. So, we set ourselves a goal to try and improve this, and our goal is to create a bug-free FPGA design in 1 hour. This sets the bar quite high, but there has to be something to aim for. We realized that our old way of working was just not future-proof, so we decided to just improve there. And what we want to present here are basically the problems we run into and how we solve them. So let's get started. How to meet this goal of building FPGA design bug-free within the hour. Well, first of all, we need to increase productivity. by reuse of code, not only functional code, so IP blocks, but also test bench code, for example. We want to automate repetitive stuff because it's often error prone as well. We want to have a unified way of working for everybody. And also we want to increase quality. Also, of course, by a reuse of code, or a reuse of bullet points, as I like to call it. Verification is an important aspect. We want our designs to be actually first time right. So it has to, when we start testing on hardware, it has to just work. Everything has to be verified in simulations, basically. And also we want to remain in control. So that means, not have as little vendor lock-in as possible, for example. And of course, productivity and quality, they all go hand in hand. So everything that has impact on quality also has some impact on productivity usually. But these two items, they are very important in how we change our FPGA design process. And actually, they are very important aspects of everything within Prodrive. So yeah, first, I'm going to tell you something about the IP library we created. To get there, first some problems. The problems we want to solve with the IP library are basically how can we share code, and also how can we ensure that this code can be used without any issues. So that means you should be able to take an IP and use it, and it should just work. It should be tested and everything. But in order to get there from our starting point, we needed to change some things. First thing was we wanted to ditch our graphical entry tools and just use plain text. There's several advantages. For example, you can use whatever editor you want. For example, Visual Studio Code or Vim or Sublime Text or something else. With pure text, you don't have any issues with source control. And actually, also the graphics are rarely missed, and they usually even got in the way, because with the graphical entry tools, you are working more on actually making a nice drawing or nice diagram than actually building your FPGA design. Then we created our FPGA standard IP repository, which was using Git enabled us to create this repository with the plain text sources. What it contains is all IPs that we built. This includes also the test benches for the IP and the documentation. And also shared test bench code, for example, is in this repository. And we chose to use a single repository for all our IPs, as opposed to just putting all IPs in different repositories. And the reason for that is that this allows us to have like a sort of latest, greatest state of everything, where everything is also tested with the latest version of its dependencies. Another important aspect we needed to do was use standard interfaces, and for this we chose XE4 Lite and XE-Stream. And we basically chose those because those protocols were adopted by the FPGA vendors when they started integrating ARM cores. So there were already a lot of IPs available with this interface. And it turns out that it's actually just a very good interface with an open specification, which generally works very well. So we adopted this as the default interface for everything, basically. And what we also do is continuous integration using Bamboo, which is a continuous integration tool which is already present at Prodrive for software development. And before merging a new IP or change or whatever to the master branch of our standard IP repository, first all tests need to pass. And currently we have 367 tests going on this IP library. And also all sanity checks must pass. And the sanity checks are some checks that we implemented to guard, for example, naming conventions, but also to ensure that there is a change log which contains up-to-date version information. And there's also some consistency checks that this version is consistent over various aspects of the repository. So now I want to talk a little bit about how we handle dependencies and also the general workflow of FPGA design. And these are also a few problems. For example, how to manage the many dependencies of complex FPGA designs. You can imagine there are a lot of sources which you need to manage. They need to be compiled. They need to be gathered from several places. So that's a challenge. How to provide a unified way of working. This has to do with the productivity improvements. If everybody uses the same way of working, it improves productivity and also reduces chances of errors, for example. And one additional problem with FPGA design is that the build and test times can be quite long, maybe multiple hours. And basically all of this we solved by using Bazel as our build system. So Bazel is a modern build system. Build system is something like Make, for example, which you can use to do builds. But Bazel is different in the sense that it has several interesting features, such as hermeticity, which basically means that all steps in a build are executed hermetically, which means they only have access to the environment and the inputs they need. And they're run in a sandbox, for example, and this makes all those build steps entirely reproducible. Parallelism is an important feature which is built in, so any targets or any dependencies that can be built in parallel will be built in parallel by Bazel. Remote execution is an important aspect for us. Bazel allows you to develop locally on your own laptop, but you can run the build or parts of the build on a different machine. Which allows us to, for example, install FPGA tooling on servers, because those are very big installs, and they usually just don't fit on your laptop, for example. But so the remote execution allows us to still develop locally, but then just do the tools that we don't have, just run them remotely. One very important feature is caching. So what Bazel does is actually cache intermediate results. And it also has a remote cache, which can be shared among multiple users. So that means that if you are work on a big project with multiple users, then basically all intermediate build results can be shared among those users. So this can also be synthesized parts of a design, for example, or maybe entire FPGA bit streams. Some background about Bazel. Bazel works with targets. And a target is actually an instance of some rule that has been predefined, and where each rule is basically just a script that does something. It can maybe, I don't know, run a tool or whatever. All targets have predefined inputs and outputs, and those inputs and outputs are actually known before any tool is run already. So before the actual work is being done, those inputs and outputs need to be known. And targets can be built. So that means you can just make a FPGA bit stream, for example. Other targets on which the target that you want to build depend also will be built if they are outdated. And targets can also be run, which is usually used in software development. So you build a piece of software and then you can run it to test it, for example. And all targets are actually placed in build files, which is text files, which use a Python-like syntax where you put all those targets. And actually, it turns out that for Bazel there aren't really any rules to create or to do FPGA design. It's all software focused. So what we did, we just built our own. We had a few design goals doing this. One of them is to provide abstraction from the tools as much as possible. Another one that was very important was make it work during development as well as in automated builds. So we want to make sure that it's actually really easy to use, this build system, and not just another chore or something that you need to do to get it running in Bamboo. And very importantly, we wanted to use a bottom-up approach. And doing bottom-up in FPGA design means that you can easily reuse parts of the design, for example. So we created our own repository with FPGA rules, and I counted them, and there are currently 57 different rules for different aspects of FPGA design. So starting simulation, running synthesis in Vivado, running synthesis in Quartus. And according to an internal survey we did, 100% of our FPGA designers actually really likes and uses the Bazel flow, so that's nice. And the way we implemented it, Bazel not just builds your FPGA, but it actually manages most aspects of FPGA design. So that includes tool chains, which version of which tool is used, licenses for those tools. Also, for example, Python environments are set up because we have a lot of internal tools written in Python. It's all handled by Bazel. And of course, all the scripts that are actually being sourced to the FPGA design tools to actually do stuff. So start a simulation or create a bit stream. There are several pitfalls, or actually one big one, and it's that new designers, they are not really able anymore to manually use the tools like Questa and Vivado that we use. So that's something we have to keep in mind here. Now on the screen I have a flowchart which shows a bit about the kind of targets that we have. So the green boxes are actually input files, so files that the user has created. So these are HDL files for some IP block, for example, and some test bench files. And then all the blue boxes, they are rules. And yeah, so they represent a target of a specific rule. And all the yellow files are actually intermediate files. So you can see that, for example, for Vivado, there's like a flow which starts with an FPGA lib. This is the basic building block for everything that we do with FPGA. We take an FPGA library, which is similar to a VHDL library, just a collection of VHDL files, system Verilog files. So this we use to basically bundle our input files. And then with the Vivado synthesis rule, we can synthesize those files, and the output is a design checkpoint, which is basically a netlist. This netlist is then an input for a next step, which is Vivado impl, which stands for implementation. And this actually does the place and route. The output is again a design checkpoint, which is a netlist. That we put in a bitstream rule, and out comes a bitstream. And all those intermediate files, they can actually be cached, for example. So if you change just a few constraints for this step, then the whole synthesis doesn't need to be run anymore, for example. And here at the bottom is basically the simulation part. So here there's another FPGA lib which contains testbed files. And this FPGA lib has a dependency on the other one, because this is the one we're going to test. And Bazel will ensure that, that those dependencies are built first. Then there is a Questa setup, which basically compiles everything and sets up a working directory which we can use. And after that comes a Questa test target, which basically runs a test. And what's very important about the way we set up those rules is that this Questa setup rule can also just be run. So the user can run this Questa setup rule, and that will just open the Questa graphical user interface, and it allows you to debug your simulation, for example. And this makes it very easy to use this also just during development, because you just write this Questa setup rule in your build file, and it will just work. Yeah, on screen now is an example of a dependency graph actually created by Bazel. And it's not intended to be readable, but the idea is to show how complex FPGA builds can become. So each box there is just a dependency of some kind, either some files or maybe a netlist or something. And you can see it's just, it's such a big network. It's just really hard to manage yourself. One problem with all those dependencies is the diamond dependency, and this occurs when some design, let's say my design, depends on two IP cores, IP A and IP B, which then both depend on a third shared IP core. And this is actually fine, of course, unless those two IPs depend on a different version of the underlying IP core, and then problems arise. And actually this is also particularly a problem for us because we chose to put all our IP in a single repository. But we found a solution for that as well. What we do is we simply flatten all dependencies recursively. This means we just, instead of multiple libraries of VHDL files, we put all the stuff in a single library, and we basically just change all the names of entities and uses and we append something to that name to make it unique, and we put everything in a single library, which is just fully portable. And that means that IP A and IP B now both contain the respective version of dependency C that they need. And every IP that we have, we release an Artifactory, which is a package management system that we already used at Prodrive. So just automatically put all our IPs in there, and they can be used as required. And now Guido will tell a bit about verification.
All right, thanks, Frey. So I'm Guido. I will tell you a bit about the verification part. So verification is all about getting our designs to work first time right. Well, of course, everybody wants their designs to work first time right. However, in practice, we experience multiple problems when achieving this. And the first thing is that testing an FPGA design on hardware is very difficult and time consuming. So iterations can take a lot of time on hardware when you have to resynthesize the design. And it's difficult to scope the right signals on hardware. Secondly, when doing directed tests in simulation, it takes a lot of time to get right coverage. So in practice, you end up with having little coverage in simulation. And thirdly, we had no standardized way of writing test benches for our designs. So in order to solve these problems, we changed our approach to verification. And first and foremost is that our approach is that we want our designs to work before we go to hardware. How do we do this? First, we replaced our directed way of testing with constrained random coverage-driven testing. And this means that we actually randomize our stimuli according to some constraints. And we think we have sufficiently tested the design if we reached a certain amount of coverage. And doing this, to do constrained random testing, we replaced our verification language VHDL from VHDL to System Verilog. Because System Verilog provides randomization and constraining this randomization. It provides keeping track of your functional coverage by making use of cover groups and cover points. And it provides the more software concept, object-oriented programming, which is very convenient when writing test benches. When you use constrained random testing, you actually increase your coverage by just testing longer or by better constraining the randomization. And you're actually not increasing your coverage by writing more tests, so you don't have to spend more time in writing tests. To get a more standardized way of working, we adopted the universal verification methodology, UVM. So this is a worldwide used methodology which is written in System Verilog. And UVM defines the way the test benches look like, how components in your test bench are named, such as sequences or a scoreboard. And it also defines the way we connect all those components in your test bench. And this provides a general way of working, and it makes it easier to communicate and review each other. Another advantage of UVM is that it's more focusing on the transaction level. And the actual pin wiggling with your design is then handled by UVM agents, which you can then reuse. And within your test bench, you're working on a more abstract level. So the use of UVM allows us also to make reusable UVM verification components. These are parts of your test bench that are made for example, for specific interfaces that people then don't have to make themselves, but we can share among each other. And Prodrive has developed quite a number of UVCs in-house. We have evaluated a number of them from external companies, but we were not satisfied with them. And therefore also, what Frey said about we like to be in control of our code, also holds for this. So therefore we have UVCs for Axie4, Axie-Stream, SPI, UART, I2C, and many more. So UVM is powerful in its own way, but For example, when you have transaction-based protocols and you have standardized interfaces, but when you have a custom interface, UVM is not that powerful. And this can happen when you have a very custom state machine or you have some arbiters. It's also difficult to do very low-level checks, for example, some timing checks, and you want to access specific pins of your design. It's more difficult to do that in UVM. So we experienced that UVM is not the silver bullet for all your test benches. And therefore, for some designs, assertion-based verification and or with formal is a very good alternative. So to get more, to explain a bit more about assertion-based verification, first, what is an assertion? So an assertion is a positive statement about your design. And the statement should actually just always hold. And mostly concurrent assertions are interesting because they are active all the time during your test. And they're very powerful in describing temporal relations. And I'll show you a few examples. One positive statement about design can be when the reset signal is high, 1 clock cycle later, the valid must be low. And in system Verilog syntax, it's described as follows. First, we say that we assert a property, and this property is sensitive to the positive edge of a clock. Then we assert that when the reset is high, we get an implication operator. So every time the reset is high, the part after this operator must always be true. And here we get the double hash 1 means a delay of 1 clock cycle. So 1 clock cycle later, valid must be equal to 0. And every time this is not true in your test bench, you will get an error. Another example, when a request signal is high, the ground must be high within 1 to 5 clock cycles. And for this, we get a similar structure in the beginning. So we again assert a property that is sensitive to a positive edge of the clock. And then when the request is high, implies that within 1 to 5 clock cycles, the ground must be high. And we see here a powerful delay range operator. And for these examples, you might think that it's also possible to write this in normal system Verilog, which is possible. But the system Verilog assertions are powerful in describing this. And it's also powerful that is describing this in a different manner than you would do in VHDL. So there's less risk that you make the same mistake twice. When using assertions, you could still use UVM for stimuli generation. So it can actually be combined. And assertions can be used both by simulation and by formal tools. And formal tools is something that we also use at Prodrive. So formal verification, that is the use of mathematical methods to prove the correctness of your design with respect to your assertions. And to illustrate what this means, on the left side here, you see some simulation traces. So when you run simulation, you start from initial state and you traverse through the state space. But you actually can only have few simulation traces. You might run multiple times, but you hope that your stimuli actually reach to a state where you encounter a bug. In the case of formal on the right side, you can see it's actually analyzing the whole state space, meaning that it starts from all the possible initial states and it will analyze then all possibilities through the state space. And then you're sure that you will encounter, that you will reach a certain state where you encounter a bug. To summarize formal verification, two key advantages is that when you have those reusable properties, everybody can use them. So you could define properties for Axie4 stream and Axie4, and then simply reuse them. And the only thing you need when using formal is your design together with those properties. So you can prove whether your RTL is according to your specification without even having to write the whole test bench. There are also some disadvantages, which is that the licenses for formal tools are very expensive. And secondly, formal does not scale well with very large designs, because a large design means that the state space is very big. And yeah, formal tools have some difficulty in analyzing this whole state space.
Okay, thanks Guido. Now I want to tell you something about some tools that we made internally. Because, well, now we have this IP library and we have ways of doing verification. And we use standard interfaces for everything. But then we start to run into some new problems, namely, how do we deal with all those AXI interconnections? So AXI is a very nice protocol, but it also has a lot of signals, so it's just a lot of work and quite error-prone to connect this in all your designs. And also, how do we handle large projects with lots of different configurations, for example? Well, in order to tackle this, we also provide a solution. We created actually our own internal tool called Merlin. This is an in-house developed Python tool suite, which basically allows us to easily integrate all those IP blocks using Python scripting. Now, you might wonder why we chose to develop our own tool, because there are some alternatives. For example, you have Vivado IP Integrator, Arteris IP, which is another commercial offering, FuseSock, which is an open source Python tool. But it turns out that all those alternatives don't really fit in our way of working. So they're not integrated in the Basel flow. Maybe might work around to get it working, but yeah, it's going to take a lot of work. And there are also several code styles that we employ. For example, we often use concatenated bus interfaces, which basically means that we have multiple, for example, AXI interfaces, but on a single set of signals. So basically all the valids become a big vector of valids, for example. And this is something that we did not find in those alternatives. So we built our own tool. The design goals for this tool was, Merlin should basically fit in any design flow, so Basel, but it should also just work standalone. It should never get in the way, you should be able to use it how you want, and it should never basically interfere with what you want to do. And also we want to make sure that Merlin does not do things that we have other tools for, such as, for example, file management. So yeah, what is Merlin in the end? Merlin is basically a set of objects describing a design. This can mean, for example, a component or a port or a bus interface connection. And these objects are really basic, and they're pretty simple actually, and allow you to describe all aspects of a design. So also, for example, parameter values. These object types, they borrow some concept from IPExact, which is a standard for an XML-based standard for IP vendors, basically. But we save our object in a JSON format. And then we have an extensive Python API to actually manipulate these objects. And the base Merlin functionality actually resembles RTL instantiations and connections. So basically entity instantiations in the VHL and signals connecting multiple entities. And we can add more functionality to Merlin easily by just building on top of it. So if you have, for example, something that can build a simple design, then you can also use that to build maybe an AXI interconnect to some specifications or whatever, and you can take that even further and further just by building layers upon layers. To give you a bit of an example, there is a bit of Python code on the screen now. This is actually the first half. Next slide will be the second half. But what you can see here, for example, is there is an AXI interconnect class being used here. Which basically sets up an AXI interconnect design with a certain write ID width and read ID width, for example. It's going to be an AXI light design in this case, and we want it to be a crossbar. And then we can very easily, for example, add master and slave interfaces to this crossbar by using the add master and add slave functions. And then in the end, when this crossbar is generated, we will just get a VHL design which instantiates the IP that we created previously, and that was tested with all those fancy UVM tools and formal properties. And that will give you a possibly pretty complex AXI infrastructure block, which will just work. And actually, this Python script, what it creates is so a design for this N by M AXI light interconnect. And the generated VHDL of that is 1385 lines. There is a bit of bloat. You could do it in less lines if you do it yourself, but to generate it, it's easier to, for example, add a net for all ports. But this gives you an idea in, basically how much work this saves. And additionally, there's also a small top-level design generated, which is also 674 lines of code. And because we have all those objects in Merlin, we cannot just generate HDL from it, for example, but we can also do different analysis. So we also have some tools to do some graphical analysis on the design, for example. So what you see now is actually a view of all the bus interface connections within this crossbar that was defined. So there are a few slave interfaces on the left, which are connected to slave connect blocks, which are basically address decoders, slave decoders. And then there are multiple internal Axi-Lite buses to multi-master blocks and then to the outputs. So this basically allows you to view that all the connections you intended are correct. This Merlin tool is something that we are actually quite proud of because it really saves a ton of work. So to conclude, basically at Prodrive we updated our whole FPGA design flow in some ways that are basically industry standards, such as using UVM and also using formal verification. But we also did some things that I think are not standard, which is, for example, use Bazel for the build flow and then also make sure that it's like a fully integrated system, which is not just building, but also allows you to easily debug test benches, for example, to make sure that everybody's actually using this. And also Merlin is, of course, a good example. And now on the screen is a diagram which basically shows all of the dependencies of the stuff that we talked about. So there is, at the bottom, there is our example script. And it's only possible because we have some Axi interconnect stuff, which is built on the Merlin base. And Axi interconnect takes data from Artifactory, which is coming from Bamboo, and it uses stuff from our RP library, where our Axi infrastructure is dependent on several other libraries, and they're all dependent on all the simulation stuff we made, so the UVCs for Axi 4 and Axi Stream, for example. And Axi Streaming UVC also integrates our formal protocol checker. And all that is based on UVM, and then again everything depends on Bazel, and even more depends on Git. So this basically gives you an idea how everything fits together. And it's also important to note that this is not something that we implemented like overnight. It's really been a process of a couple of years already, starting in I think 2017 or something. We have been working on it, and now it's really coming together. And now we can really ask ourselves the question. Can we build a bug-free FPGA design in 1 hour? And the answer is, it depends. So if we, for example, such an interconnect design, the answer is definitely yes. We can make an interconnect, Axi interconnect, which is as complex as you can imagine, and it will just work because it's tested and all the components are tested, and it will work within the hour. So that's it, basically. Thanks for watching.